Hi everybody. This video is an introduction to integration, and it's the first video in our integration series. To begin, integration is the inverse of differentiation. We've seen previously that with differentiation we can start with a function and we can find its instantaneous rate of change. So with integration we can start with an instantaneous rate of change of a function, and then we can work backwards to find the function. And to describe this process in a little bit more detail, integration allows us to determine a function f of x from one of its known values and its derivative, dy dx. So here we're going to introduce a new definition. We're going to talk about indefinite integrals. So when we start with an instantaneous rate of change and we work backwards using integration to find a function, the result is called an antiderivative. A function capital F of x is an antiderivative of a function f of x if the derivative of that antiderivative capital F of x is equal to f of x for all values of x in the domain of the function f, so in the input set of the function f. Down at the bottom of the slide we got a specific definition for indefinite integral and an equation to represent it. The set of all antiderivatives of a function f is the indefinite integral of f with respect to x. So to look specifically at this equation down here, first of all, there's a symbol that you might not have seen before. Right at the start, that elongated S symbol, so what that is, that's an integral sign. And we read that equation as the indefinite integral of f of x with respect to x, that's the x part, that's equal to capital F of x plus c. So in the next minute or so, we're going to talk a little bit more about that plus c term. And also, just to reiterate, that capital F of x there on the right hand side of the equals, so what we've got there is that's one of the antiderivatives, and then we've added a plus c. So next we're going to see why that's there and what it is. So here goes. Many different antiderivatives can all have the same derivative. For example, for capital F of x is equal to x squared, or capital F of x is equal to x squared plus 3, or capital F of x is equal to x squared minus 4. So if you differentiate each of those with respect to x, you get the same result each time. The derivative of each of those functions, it's 2x for each one of them. The derivative of x squared is 2x. And if you derive with respect to x squared plus 3, that's 2x as well, and so on. So if we integrated 2x, if we worked backwards, we get x squared, but that's only one antiderivative. By the definition of indefinite integral, we want to somehow represent the set of all antiderivatives. So to do this, to represent this, when we find the indefinite integral of a function, we find one antiderivative and then we add a constant of integration to it, that's what that capital C is. That's our constant of integration. So then our result capital F of x plus c that one antiderivative plus our constant of integration, that represents the set of all possible antiderivatives of f of x. It represents capital F of x equals x squared, and it represents capital F of x is equal to x squared plus 3. If our value of capital C is 0, it represents capital F of x equal to x squared. If our value of capital C is 3, it represents capital F of x is equal to x squared plus 3, and so on. So we've talked a little bit about integration, and we've given a definition of what an indefinite integral is. So now we're going to show you the process of integration, and we're going to highlight the fact that integration is the inverse of differentiation. We're going to differentiate a function, and then we're going to integrate to get back to that function again. So we're going to start with a function, and we're going to differentiate it to get the function's instantaneous rate of change. And then we're going to use integration to calculate the function from the rate of change and one of the known values of that original function. So here we go. We want to find initially the derivative of capital F of x is equal to x squared. And we're starting off with, we have a known value. We know that capital F of 2, we know that that's going to be equal to 4. So initially, to differentiate, we're going to use the power rule. If capital F of x is equal to x to the n, then d capital F dx, that's going to be equal to the derivative of x to the n with respect to x, which is equal to nx, where x is raised to the power of n minus 1. So knowing that capital F of x is equal to x squared, the derivative of x squared with respect to x, well, by the power rule, that's equal to 2x when we work that out. So the instantaneous rate of change of capital F of x, where capital F of x is equal to x squared, that instantaneous rate of change, that's equal to 2x. So that was the starting with a function and then differentiating it to get its instantaneous rate of change. Now we can use integration to start with the rate of change, which we're going to represent with a lowercase f of x, which is equal to 2x. And then we're going to work back to the function capital F of x is equal to x squared by integrating and using its known, one of its known values. So to start off with, we're going to find the indefinite integral. So we've got capital F of x is equal to x squared from the initial function we began with. We know that its instantaneous rate of change, f of x, that's equal to 2x, and we have a known value, capital F of 2 is equal to 4. So what we want to do is we want to start with f of x is equal to 2x, and we want to get back to capital F of x is equal to x squared. We're going to start doing that by integrating. So to integrate f of x, we want to find a function that has a derivative equal to 2x. This will be one antiderivative, and we're going to represent it by capital F of x. So by our definition, the indefinite integral of f of x with respect to x, that's going to be equal to capital F of x plus c. So it'll be equal to one antiderivative plus a constant of integration to represent the set of all antiderivatives. Well, we know that one antiderivative of 2x, well, one of its antiderivatives is a x squared. So we can substitute that in, and we've got the indefinite integral of f of x with respect to x. That's equal to x squared plus c. So we've added that constant of integration to represent the set of all antiderivatives. So we have the set of all antiderivatives, x squared plus c. But we want to find specifically one antiderivative, the function that we started with. And to find our original function, we substitute in our known value and we solve for c. So we had our known value, capital F of 2, is equal to 4. So we use that information. We have the set of all antiderivatives, x squared plus c. If we substitute a value of 2 in for x, we get 2 squared plus c, and we have, well, that is going to be equal to 4. So now we can solve for c, the constant of integration. So if we take that 2 squared over to the other side of the equal sign and we keep our value of capital C there, we get that the constant of integration, capital C, that'll be equal to 4 minus 4, which is equal to 0. So the value of our constant of integration in this case, it's actually 0. So we can substitute that in. Capital F of x is equal to x squared plus c, which is equal to x squared plus 0, which is equal to x squared. So we've done it. We've used integration to go back to our original function that we began with. Here showing how we use integration and demonstrating that integration is the inverse of differentiation. So we've covered a few things here. We've talked a little bit about integration, and we've learned what an indefinite integral is, and we've seen an example how to calculate them. Next up, we're going to learn some rules that allow us to calculate a range of different integrals, and later on we're going to see a range of practical applications of integrals. So you can do so much stuff with this. It's incredibly useful. In particular, we're going to see how an integral can be used to represent the area between a curve and the axis. And later on, we're going to see a lot of other different applications that stem from that as well. Thank you for your time watching this video, and see you next video.